Okay, so we're going to jump right into tonight's material because we have a lot to go over. So we're going to um, start with the challenge problems from last session, which now was almost 2 weeks ago, a little bit under. I hope everyone had a good spring break. And so again, jumping in, I think there were 5 challenge problems from last Wednesday, so we'll start with those before jumping into chapter 18, which is electrochemistry. Okay, so the first 2 problems were actually almost the exact same problem. In both of them, you're asked to find the standard change in Gibbs free energy, or delta G naught. They're the same thing. Okay, and you were told that the reaction for each was run at 25 degrees Celsius, which is 298 Kelvin. Okay, and you were also given the equilibrium constant K. Okay, so again, problems 1 and 2 you actually would have solved in the exact same way. Okay, the only difference that you would have had is the value, your equilibrium constant value. Those were different between the 2 problems, but the temperature and R, which is a constant, should have been the same. Okay, so for both of these problems, you would have used the equation delta G naught equals negative RT times the natural log of K, right? Because when you're at equilibrium, you're going to use this equation. And so when you plug in these values for number 1, you would have found that delta G naught is positive 624.8 joules, so about 625 joules. And for 2, it would have come out to about positive 426 joules. That wasn't an answer, however, you had to convert it to kilojoules. And so the correct answer would have been 0.426 kilojoules. Right? It convert from joules to kilojoules, you just divide by 1,000. Okay, question 3 was a little bit more theoretical. There's a bunch of great examples of these in lecture as well, of kind of predicting the sign of delta S, and you definitely could see this as maybe one multiple choice question. So just generally looking at these, what should the sign of delta S be? So for A, we have water vapor. So it's in the gas phase, and it's going to condense down to a liquid, right? So entropy, or delta S in general, we know increases as we go from it increases with temperature, but it also increases as you go from a solid to a liquid to a gas. Okay, so for A, our reactant, water vapor in the gas phase, right, will have a relatively high S value or entropy value. It's going to have a relatively high amount of disorder because it's in the gas phase. While liquid water, because it's in the liquid form, it does have a bunch of disorder and some freedom, but not as much compared to the gas phase. Okay, so on the product side, we're going to have a lower amount of entropy compared to the reactant side. And so when you solve for delta S, which is products minus reactants, A would give you a negative delta S value, or we would predict that, right? We don't have the real values, but based on the equation, it should be negative. Now in B, right, we're going to do the same exact thing. So here we have 2 moles of dihydrogen sulfide gas reacting with solid carbon to form methane gas and solid sulfur. Okay, and so whenever you're looking at an equation like this, where we have some combination of gas and solids in this case, or liquids, right, solids have a super low amount of entropy, especially compared to gases. Okay, so if you ever see solid and gases in the same equation, I would kind of just ignore the solids. Okay, and so what you should do here is kind of say, in general, I have 2 moles of gas on my reactant side and 1 mole of gas on my product side. Okay, so when you're comparing directly moles of gases, right, more moles equals more disorder or higher entropy. Okay, because again, if you have more moles of it, it can just do more. It can react more, bump, collide, whatever. It just has greater amounts of disorder. So we would predict, because we have 2 moles of gas on the reactant side in part B, that the reactant side is higher disorder compared to the product side, and therefore when we find the delta S, we would predict that B would also have a negative delta S. Okay, so I'll leave this up for just 1 second, but again, this basically is just saying the same thing I just verbally explained. Okay. So if there are no questions up to this point, we'll move on to number 4. Something I overlooked in this problem, and I do apologize for, it would have technically made it impossible to solve it, is a temperature. I did not give a temperature, and you did need one. And so ideally, you would have used 298 Kelvin or 25 degrees Celsius. But if you got stuck, that is my fault. A temperature should have been provided. Okay, so in this problem, you're told that you have a reaction vessel. You're going to mix nitrogen and hydrogen gas along with carbon monoxide, and you're going to produce nitrogen monoxide and a hydrocarbon. Okay, and you're given some reactions down here. And so remember that a hydrocarbon is just a compound that only contains hydrogen and carbon. And so the hydrocarbon that they're referring to in the problem has to be C2H6. Right, that's the only hydrocarbon present in either of these two equations. Ethane, but yeah. And so when you run this reaction, you find that the change in Gibbs free energy is 375 kilojoules. And so based on this, I wanted you to find both the reaction quotient and equilibrium constants. Okay, and so this is one where you actually need to manipulate these equations down here to match the equation described in the problem. Okay, so starting at the top, right, the first sentence of the problem, I say nitrogen gas, which occurs in the diatomic form, will react with hydrogen gas, which also occurs in the diatomic form, and these are going to react with carbon monoxide to produce nitrogen monoxide and a hydrocarbon. Now the states of all of these, so hydrogen and nitrogen, we pretty much know are gases, but if you're unsure the states of carbon monoxide, nitrogen monoxide, or the hydrocarbon, I kind of got the states of matter from these below equations, right? We can see here that our hydrocarbon is clearly in the gas phase. So if you're confused about how I knew the phase of each of these compounds, I pretty much got it from the two given reactions. Okay, now to get to the next line, all I did was I took the generic reaction that was given in the first sentence of this problem, and I just balanced it, right? So in order for the hydrogens to balance, I needed to have a coefficient of 3 in front of it. I needed a coefficient of 2 in front of both carbon monoxide and nitrogen monoxide for every single element to perfectly balance out. Okay, now that I have a completely balanced chemical equation that was described in that first sentence, I'm going to take those two sub-reactions given to me on the previous slide, and I'm going to try to make this reaction that was described in that first sentence. Okay, so this is very similar to Hess's law, which we did back in chapter 6, I think was thermochem last semester. Okay, and so if you ever need to make what I call a goal reaction, which is this reaction at top, and you have multiple sub-reactions, which were the two reactions given on the previous slide, my suggestion is always identify some compound that is unique to each sub-reaction. Okay, so in sub-reaction A, and again, this is just the first reaction that was given in the problem on the previous slide, we had 2 moles of ammonia, which go to nitrogen gas and hydrogen gas. Now, my unique compound that I identified in this sub-reaction is nitrogen gas. When I compare nitrogen gas in this sub-reaction to the nitrogen gas in my goal reaction, right, I can see that they both have a coefficient of 1, but that in order to get to my goal reaction, I need to change my nitrogen so that it's a reactant, right? It's currently written as a product. And so this indicates to me that that first sub-reaction that I had written, right? I want to flip it so that now I have nitrogen gas that reacts with hydrogen gas to produce ammonia. And so remember that when we flip an equation, right, products become reactants, reactants become products. Whenever we do that, all we have to do to the delta G naught is change the sign. Okay, so my new delta G naught value for this first subreaction should be negative 32.96 kilojoules. Okay, now I'm going to do the same thing with the second subreaction. Okay, so that subreaction said that 2 molecules of ammonia would react with 2 molecules of carbon monoxide to produce 2 molecules of nitrogen monoxide and my hydrocarbon. Okay, so personally, I could have chose many things to be my unique compound in this subreaction, but I chose to focus on nitrogen monoxide. Okay, so when I compare nitrogen monoxide in my second subreaction to my overall goal reaction, right, the coefficient for nitrogen monoxide is 2 in each case, and it's a product in each. Okay, so because these exactly match each other, this indicates that I do not need to manipulate my second subequation, right, which I label B. Okay, and the given delta G naught value for this second subequation was 450 kilojoules or so. Okay, now that I've manipulated my two subequations so that they kind of match, or at least some of the compounds match how they appear in my goal reaction, I'm going to combine my two subequations. Okay, so I'm going to combine my manipulated subreaction for A and my subreaction for B, which we didn't need to manipulate. And when I combine them and cross out any compounds that appear on both the reactant or product side, I'm left with this net overall equation, which you'll notice perfectly matches the goal equation that I had at the top. Okay, so that tells me when you combine them and get the same equation as your goal equation, that tells you that your manipulations that you did above were correct. Okay, so now that I've correctly manipulated my subreactions, I can find the delta G naught value for this overall goal equation by adding together my delta G naughts of my manipulated equations. So my delta G naught in this case will be equal to negative 32.96 kilojoules plus positive 450.37 kilojoules. And so delta G naught here would equal 417.41 kilojoules. Sorry, I also did not, oh, it's on the next, I apologize, it's on the next page, the reaction quotient. I forgot for a second. I thought I didn't do it. Okay, so the question wasn't what's delta G naught for this equation, right? I actually asked what's the equilibrium constant. Okay, so what's K? So now that we have delta G naught for our overall equation, we want to find an equation that utilizes both that delta G naught value and our equilibrium constant. And so the equation we're going to use in this case is that delta G naught is equal to negative RT times the natural log of K. Okay, now delta G naught here, we just solved for above. That's going to be that 417.41 kilojoules, right? We're going to plug in R, which is 8.31. We're going to plug in our temperature, which is 298 Kelvin. And that, again, is multiplied by the natural log of our equilibrium constant, K. Now, something really important to note here is that delta G naught is 417 kilojoules, right? That R value, 8.31, is in terms of joules, okay? And so you can't directly compare these sides, right? You have to convert both sides in terms of kilojoules or both sides in terms of joules in order to solve for our equilibrium constant. And so all I did is I converted my delta G naught to joules. And so it's 417,410 joules is equal to negative R times T times the natural log of K. And when you solve for the natural log of K, it ends up coming out to 6.26 times 10 to the negative 74th power. Okay, so it's incredibly, incredibly small. Okay, if If you have any questions on the first part, please feel free to put it in the chat now as I go over the second part, which is the reaction quotient portion of this question, and then I can circle back to any questions. Okay, so that first slide showed us how to solve for the equilibrium constant for this. Okay, but we were also asked, what is the reaction quotient, right? And we calculate the reaction quotient when we're not necessarily at equilibrium. Okay, and so in thermochem, whenever we are talking about the reaction quotient, we're going to associate it with this equation, which is saying delta G is equal to delta G naught plus RT ln Q. Now remember that delta G and delta G naught are not the same thing, right? Whenever we see this superscript circle, which we say that's what naught is, right? That is calculated at very specific conditions, okay? And the reason why we have this is really to be able to compare values and reactions to one another. However, again, it's calculated under very specific conditions. And so often it doesn't truly mimic or show real reactions that we're actually running. Okay, so delta G is the real change in Gibbs free energy of the reaction you are running in front of you, right, in theory. Okay, and so in the problem, we were basically told that the actual change in Gibbs free energy for this equation was 375 kilojoules, right? So that statement, I think it was the second sentence of this problem, is referring to the delta G value, okay? Now the delta G naught is what we calculated in the first part of this problem, so it's 417 kilojoules or so. That R value is still going to be 8.31. Our temperature is still going to be 298 Kelvin, and that's multiplied by the natural log of Q. Okay, now again, this R value, 8.31, is in terms of joules, while my delta G naught and delta G are in terms of kilojoules. So all I do is I convert those values to joules so that they can be directly compared to this 8.31 value. Okay, from here it's just a bunch of algebraic manipulation, but when you solve for Q, it comes out to 3.65 times 10 to the negative 8th. Okay, are there any questions on this problem before I move on? And if there aren't, can a few people just indicate that to me? I know this problem is definitely on the harder side. Awesome. And if there are questions, I'm happy to circle back. This is the last problem that was given out that we'll go over right now before jumping into our new material. And so this is chapter 17 for you guys is only going to appear as multiple choice section. However, this type of question, if you had a long answer section, is like your very classic chapter 17 long answer question. And so here you're given a chemical formula, a change in enthalpy, so delta G for this reaction, and then you're given a table with entropy values, S values. And based on this information, we want to find what's the delta G naught at 25 degrees Celsius. At what temperature will this reaction be spontaneous, if that's applicable? And then lastly, what is the equilibrium constant for this reaction at 25 degrees Celsius? Okay, so we were directly given a delta H for this equation. And so in order to solve for delta G, right, we're gonna wanna focus our attention on finding what the change or delta, the change in entropy or delta S is for this reaction. So the change in entropy is going to be equal to the sum of entropy of our products minus the sum of entropy of our reactants. Okay, and again, be very careful to make sure you're doing products minus reactants. Okay, and so I input these values, right? So in this second bracket, these are all of our reactants. And I would just say, note how I take these values from the table. Sorry, I don't really remember the equations. Let me go back for a second. This would be liquid nitric acid, which I don't really know if it's a thing, but liquid nitric acid here was the product. Its entropy value is 155.6, but notice I multiplied it by 2 because that's its coefficient in the balanced chemical equation. Okay, so remember when you're inputting these values to multiply each compound by its respective coefficient. Okay, and so when we solve for the delta S naught of this equation, it comes out to negative 650.8 joules per Kelvin. Okay, and our delta H was given, it's positive 47.3 kilojoules. So now that I have my delta S and my delta H, I can find my delta G through this really useful equation, right? Delta G naught equals delta H minus T delta S. Okay, now you'll notice here that my delta H value, I converted from kilojoules to joules, right? So now it's 47,300 joules. And from that, we're going to subtract our temperature, 298 Kelvin, times our delta S value. So what we find is that the change in Gibbs free energy for this problem is about 241 kilojoules, right? It's a really big positive number. And remember that positive values in thermochemistry indicates that this is not a spontaneous reaction. Okay. So question B asks, at what temperature would this reaction be spontaneous? So above, we found that at 25 degrees Celsius, this reaction is definitely not spontaneous. But are there temperatures that could make this reaction spontaneous? And so to do this, I kind of write my generic equation, and I just fill in the signs of delta H and T delta S. Right, so delta H is positive 47.3 kilojoules. So it's a positive number. Okay, and from delta H, we are going to subtract temperature times our delta S. Now, temperature, which is recorded in Kelvin, right, has to be positive, right? You cannot go into the negatives on the Kelvin scale. So temperature is a positive number, and delta S is a negative number, right? Negative 650 joules per Kelvin. And so when we multiply T times delta S, that's going to be a negative number. So when you have a positive number and you subtract a negative number from it, it's really like adding two positive numbers together. And so basically, we find out that no matter what temperature we are at, delta G naught will always be positive. Therefore, the reaction will never be spontaneous. Okay, the last step of this problem was just to solve for the equilibrium constant. So again, we're going to use this equation, which we used in the last problem as well. Our delta G naught here was 241 kilojoules, which I just converted to joules, right? So I used the longer joule version. That's going to be equal to negative R, 8.31, times temperature, 298, times the natural log of K. Through algebraic manipulation, we can find that the equilibrium constant should be 4.93 times 10 to the negative 43rd. Okay, so if people don't mind just signing in right now in the chat with your net ID to indicate that you have no questions. If you do have any questions on any of those problems we went over, please feel free to let me know. Because I'm happy to go through anything further before we start to move on. Okay. So I think that's everyone. So just to quickly go over our SI schedule. So tonight we'll be going over the majority of chapter 18. I will do my best to get through the majority of it. Everything that I have prepared for tonight corresponds to videos 1 through 8 on this chapter. So I think there's a total of 10 videos. Anything from video 9 or 10 that is hugely significant will definitely appear on Wednesday. Okay, but we will definitely get through the vast bulk of the chapter tonight. On Wednesday, we'll be doing our chapter 17 and 18 review. So how I'll probably formulate this is it'll kind of look a lot like a normal review session where we'll start and go through the main topics in chapter 17, then move on to chapter 18. Okay, but within that review, right? If there are chapter 18 topics we haven't really touched upon yet, it'll just be an elaborated section of that review. Will be like dedicated. So I'm not going to go through the new topics from chapter 18 and then do a 17 and 18 review. The whole SI session will be in the format of a review. And then when we get to any topics we haven't yet covered in SI, we're just going to spend much longer on them. Okay, and probably go through some example problems. Okay, just so you know how that's going to kind of run. And then on on Friday, you have your multiple choice exam on these chapters. And then next week, which hard to believe because it was just spring break, but next week is the last week of classes. And so we'll be focusing on the last chapter, chapter 19, nuclear chemistry, maybe some wrap up on Wednesday. And yeah, then you're done with the course. I am not decided yet if I will be able to do anything for a final review. So that will be left kind of to be determined. Okay, so these are the main topics from chapter 18, namely the ones we're covering tonight. Right, so we're going to go through an introduction to electrochemistry, then look at an electrochemical cell, have some quick notes on electric circuits or just, circuits in general. Then we're going to go into types of electrochemical cells, which are really important. Talk about our manipulations of cell potential, or E. Then some more important equations, or going into some important equations, integrating what we've learned. So on that slide, we'll look at how cell potential relates to change in Gibbs free energy and our equilibrium constant. Then we'll look at the Nernst equation before looking at other units within electrochemistry. Okay, so I'm going to jump right in just because, again, we have a lot to go through. So electrochemistry is just it's studying the conversions of electro and chemical energy. And really how you can think about this is it's applied redox reactions. And I just want to draw your attention back to chapter 4 from 1127. So chapter 4 in 1127 had 3 main types of reactions. We looked at precipitation reactions, acid-base reactions, and redox reactions. Okay, and so kind of just realize that everything that we've been doing recently in this course is just looking at harder and more complicated examples of these same reactions, right? The acid-base reactions that we did last semester appeared as buffers and titrations and equilibrium this semester. Precipitation reactions from last semester, which was the formation of a solid, turned into our KSP and KF chapter 16 this semester. And then lastly, redox reactions that we saw last semester, we learned how to balance half reactions. They come up in an applied version here through electrochemistry. So just to remind you of some of your very important terminology, right? Oxidized and reduced. Okay, so oxidized, it's referring to an element, so a specific element can be oxidized or reduced. And if the element is oxidized, it means it lost electrons or had a loss of electrons. Okay, and so if an element loses electrons, it's going to increase in oxidation number. Okay, now if an element is reduced, it is going to gain electrons, or it has a gain of electrons. Okay, and if it's gaining electrons, the reduced element is going to decrease in oxidation number. Now, there's many ways to remember this. There's Leo the Lion says GER or oil rig. Those are mnemonics that people have used and the professors have often cited in the past. However, how I remember it, if this is helpful to you, I just think reduced, that word in general means to lower. And so if an element's being reduced, that means its oxidation number's going down. And if your oxidation number is going down, you're gaining electrons. So I just remember reduced means oxidation numbers going down, which means oxidized means the oxidation numbers going up. Okay, I apologize for kind of the quality of this image. It was a screenshot from one of the lecture videos, but I just wanted a decent diagram of an electrochemical cell. Okay, so every electrochemical cell, and I have that slide on the next page that kind of verbally talks about these different portions. Electrochemical cells have two different electrodes, right? We have our anode and we have our cathode. Okay, so you can often think of it as two jars. And between these anodes and cathodes, you'll typically have two metal bars, one in each. Okay, and they'll be connected by a metal wire. Okay, this metal wire is going to allow electrons to move from our anode to our cathode. Okay, electrons will always move from the anode to the cathode. Okay, now what you'll also see between our anode and cathode is a salt bridge. Okay, now this salt bridge allows ions to travel from one side to the other. And the purpose of this salt bridge is really just to, it kind of counterbalances charge differentials that occur due to the redox reactions occurring. Okay, and so I'm going to skip to the next slide where it just kind of summarizes these portions. So again, the components, the salt bridge, ions move there, and again, that's to help balance charge, while the wire allows for electron movement. And electrons will always, always move from the anode to the cathode. Okay, now something that's really important to note is at the anode, right, oxidation will always occur. Okay, at the anode, oxidation will always occur. At the cathode, reduction will always occur. Okay, and this kind of makes sense. I'm just going to go back to the diagram for a second, right? So we said electrons transferred from the anode to the cathode. Well, that makes sense. At the anode, we just found out that oxidation occurs. Well, when oxidation occurs, electrons are lost. Okay, so the electrons are lost during the oxidation that occurs at the anode, and those electrons transfer to the cathode where reduction occurs. And reduction, we gain electrons, right? So we're gaining those electrons through this wire. Okay, now I know your professor, Dr. P, gave some suggestions on how to remember this, that oxidation occurs at the anode, reduction to the cathode. It's not the best trick. I'm not in love with it. However, I've always remembered it, that the anode, or anode starts with a vowel, and so does oxidation. Okay, so the ones that start with vowels occur at each other. So oxidation at the anode, while cathode, or the C that cathode starts with, and R, which starts reduction, right? Those both start with consonants. Okay, and so again, I don't love that trick to remember it. However, that has helped me. I would definitely recommend, because you guys get a cheat sheet, to write this on your cheat sheet, because it's super important. I can't emphasize how important it is that you know that anode is where oxidation occurs, cathode is where reduction occurs. Okay, now in lecture, this is something that comes up quite a bit. There is a proper notation for electrochemical cells. Okay, and so just a generic way to write this notation would be some compound, I'm going to list it as A, with a line, then another compound, B, and then there's going to be two lines followed by two more compounds that are separated by a single line. Okay, now something to note is that A and B and M and N are typically the same, they're the same element, okay? They just change in their charge, okay, and often their state, okay? And so notice that A and B are pretty much the same compound, M and N, but they're gonna be separated by a single line, while these double lines separate completely different compounds. And we'll look at that with the examples coming up. Now, Dr. P mentioned that this double line represents the salt bridge. I've always personally thought of it as it's just separating our anode portion and our cathode portion. Okay, so the anode portion will always be written on the left. The cathode portion will always be written on the right. Okay, that is a must. You cannot interchange them. Anode on the left, cathode on the right. Now, this singular line between A and B and M and N represents a phase barrier. Okay, so typically in redox reactions, right, you will have a comp or an element in the solid phase, and you'll also have it in an ion phase, right? It'll have a charge. And so typically you will see that on either side of this phase barrier. Okay, now typically when you write these, right, A and M, which for your anode and cathode is kind of the left portion, those are typically the reactants in your redox reaction. While where B and N are, those represents the products in your redox reaction. Okay, so this might make a little bit more sense with some examples. Okay, so let's look at the example where manganese solid reacts with iron 2 plus in the aqueous phase to produce manganese 2 plus iron solid. Okay, so looking at these individually, manganese has an oxidation state of 0 originally, and then it goes to positive 2 on the product side. So this tells me that manganese is oxidized. Okay, iron goes from oxidation state of positive 2 down to 0. That indicates to me that it's reduced. Okay, now remember that at the anode, oxidation occurs. So that indicates that on the left side of this double line, which is my anode portion, I'm going to write my manganese information. Okay, so in this first spot, I'm going to put how manganese appears on my reactant side, so manganese solid. And on the right side of this single line, but notice still on this anode side, I'm going to write how manganese appears on the product side of my reaction. So manganese 2 plus aqueous. Okay, sometimes you'll see the states of matter included, other times not. I today chose to include them. Okay, now that we've written our anode portion, we're going to write our double line, which separates our anode portion from our cathode portion. So our cathode portion is where reduction occurs. Okay, so on the left-hand side of this singular line for my cathode, I'm going to write how my reduced element appears on the reactant side, so is iron 2 plus. Okay, now on the right side of this single line, I'm going to write how iron appears on the product side, so iron solid. Okay, so this would be the correct way, or the correct notation, to write this above example redox reaction. Okay, now in lecture, there was also an atypical example given, and I just kind of wanted to explain it a little bit. So I actually used the same exact example given. So it was zinc solid plus 2 cobalt 3 plus goes to zinc 2 plus 2 cobalt 2 pluses. So zinc here got oxidized while cobalt got reduced. Okay, so again, zinc, which was oxidized, should appear on the left-hand side of the double line because it should occur at the anode. And so our reactant for zinc should be zinc solid. Our product is zinc 2 plus aqueous. And so I write those respectively. Okay, that was the exact same as what we did above. Now, when we look at our cathode portion, it actually gets a lot more complicated. Okay, because we typically write this single line at a phase barrier, right? Which means we change from one state to another, right? Aqueous to solid, or solid to aqueous, I guess, if you're looking at zinc in this atypical example, right? That was the phase transition from solid to aqueous. But cobalt here on reactant and product side is in the aqueous phase, right? There is no phase change. They're in the same phase. So whenever that happens, right, you're going to write the reactant and product version of that element next to each other with a comma between, right? So on the reactant side, it was cobalt 3 plus, so I'm going to write that first, and then I'm going to write comma, and then I'm going to write right next to it my cobalt, how it appeared on the product side. So cobalt 3 plus, comma, cobalt 2 plus. Then I'm going to draw a line, that single line for phase barrier, and I'm going to write PT for platinum. Okay, and the reason why you do this is the platinum there is actually going to be a solid bar. It's kind of like a substrate for it, I guess you could think of it. But how it's applicable to notation, definitely if you want more clarification, ask your professors. They're probably more well-versed in how to write the notation with platinum. But basically, right, if you do not see an element change phase, like we did for cobalt 3 plus and cobalt 2 plus in this circumstance, right, you're always going to have Pt or platinum in your equation. And so if this occurs at the cathode, like it does in this example, you're going to write Pt or platinum on the far right. So it's going to be this last portion that's platinum. Okay, if this instead occurred at the anode, right? So if it occurred on the anode, right? Then we would have written Pt or platinum all the way to the far left, right? So it would have replaced this first portion, and my two elements with a comma between would have been the second. Okay, just something to be familiar with in case it comes up. It's definitely not your most typical thing. However, it's been introduced in one or two examples in lecture, so definitely be familiar with it. Are there any questions before I start going on to this material on this slide? All right, so just jumping in, there's just a couple quick points that I want to make on this slide. So electric circuits. So circuits in general always need to connect or be complete, right? I'm sure we've all in middle school or high school made little circuit boards. You know, you just had a battery, some wire, and you attach it to a light bulb and it glows, right? And you know that if the circuit's not complete, that light bulb won't turn on, it won't be working. However, if everything's touching each other properly, the circuit will be complete, electricity or electrons will flow, and the light bulb will turn on, right? In these electrochemical circuits, right, we have a complete circuit, okay? And it's accomplished by both the wire, which allows electrons to move, but it's also completed by the salt bridge that allows the movement of ions. Okay, now the driving force behind these electrochemical cells is what we call cell potential, and we'll denote it with the letter E. Okay, now the cell potential, or E for the entire cell, is going to be the sum of our two half reactions, our reduction half reaction and our oxidation half reaction. Okay, so that's this equation shown here. And if the cell potential, or E, value of the cell is greater than 0, so if it's a positive value, that's going to indicate that the reaction, or the full redox reaction is spontaneous and favorable. Okay, if the E value or the cell potential value is negative, right? So if it's less than 0, that's going to be a non-spontaneous and non-favorable reaction. Okay, now on right here, I said that the E naught of cell, so our standard cell potential, is equal to our cell potential of reduction, our reduction potential plus our oxidation potential. And you'll get these values, I'm sure you saw it lots of times in lecture, from a table just like this. Okay, so you'd be given this table, or at least the given reactions and their respective reduction potentials. One thing to note is that all of your reactions are written in terms of the reduction potential, okay? None of them are given in terms of their oxidation potential, okay? So you're actually gonna have to derive that for one of your equations, and you'll do that just by flipping your oxidation equation. And I do have an example coming up, so we'll look at that then. Okay, so 2 slides ago, again, I said that spontaneous electrochemical cells have positive E values, while non-spontaneous ones have negative E values. Okay, and so any cell that's spontaneous, so has a positive E value, can be referred to as a voltaic or a galvanic cell. Okay, by definition, you will never have a galvanic cell that has a negative E value. Okay, if they say voltaic or galvanic, it automatically means that the cell potential, the E value for the cell, will be positive. Okay, and so again, to solve this, we'll have to flip one of our half reactions to find the oxidation potential of that reaction, and then add them together to find our overall cell potential. Okay, we'll talk about that on the next slide. Okay, now voltaic and galvanic cells represent a battery, right? Imagine a Duracell battery that you plug in to maybe your TV remote or like an Xbox controller, right? They have these electrochemical cells in them, right? And they are voltaic and galvanic cells, right? They undergo redox reactions and spontaneously produce energy that is then used for your remote control to work. Okay, so batteries are voltaic and galvanic cells. We also have something called an electrolytic cell, which has a negative E value. Okay, and electrolytic cells use electrical energy or heat to push a reaction against the gradient, the natural gradient. Okay, so it's unfavorable. Without this input of energy, it wouldn't go this way. Okay, and there's a term that we have called electrolysis, which is the process of pushing an unfavorable reaction forward by using electric power. Now, electrolysis is the process that occurs every time you plug your phone in at night to charge, right? Our phone battery has a natural gradient, right? It acts as a voltaic or galvanic cell, right? That a reaction occurs, allowing you to do everything you need to on your phone. However, when your battery dies or starts to run low, you plug it into the wall, and that input of energy from the wall through your charger into your phone is pushing the redox reaction in your phone, occurring in the battery of your phone, against its gradient to recharge the battery. Okay. And so in order to solve these problems, or for the cell potential, we need to know how to manipulate our reduction potential equations. Okay, and this will make better sense on the next couple slides when we do some examples, but if you ever need to flip an equation in this chapter in electrochemistry, right, all you do to E, your reduction potential, is you change its sign, right? You multiply it by -1. If it was a positive value, it's now going to be a negative value. If it was a negative value, it's now just going to be a positive value. Okay, all you do whenever you flip an equation in electrochemistry is change the sign on E. Okay, if you ever have to multiply an equation by a certain coefficient, and this one I would definitely star, whenever you multiply a half reaction by a certain coefficient, it has no effect on your reduction potential. Okay, you ignore it. And that's because reduction potential is an intensive property. Okay, it doesn't really have to do with how much of your starting reactant you have, right? The reduction potential won't change. Okay, and then if you ever add equations together, right? Whenever you add our half reaction together, all you do is you add these E values together. Okay, now let's apply this to a problem. Actually, I think two problems. Okay, so this asks, what's the standard electric potential of the following cell, and what type of cell is it? Okay, so here we're given, I couldn't find straight single lines, so I had to do dashed lines. But here we're given an electrochemical cell in terms of standard notation, and we have to interpret this, right? So the left-hand side, which is our cadmium equation, that corresponds with the anode. And at the anode, oxidation occurs. Okay, magnesium, on the other hand, right? This is on the right-hand side of the double line. So this is the cathode, where reduction occurs. Okay, so because we know magnesium's being reduced, and this half reaction for magnesium is already in terms of its reduction potential, we don't need to change this magnesium equation. Okay, but cadmium, which is written in terms of reduction below, is being oxidized. So this indicates to us that we have to flip this cadmium half reaction and change the sign on its cell potential. Okay, so again, that's kind of what I described. And so as you'll see, I kept my magnesium equation exactly the same, right? Magnesium 2 plus 2 electrons goes to magnesium solid, and I wrote its reduction potential. Now my cadmium equation, you'll notice I flipped. And when I flipped this equation, I wrote the E-oxy, so the oxidation potential of this reaction. And so it comes to positive 0.402, right? Because I had to change the sign when I flipped the equation. So now that I have my magnesium equation in terms of reduction and my cadmium equation in terms of oxidation, I would add these two equations together. And when I add these two equations together, I can find the E0 value of my cell by taking the reduction potential from the magnesium equation, adding it to the oxidation potential from the cadmium equation, and that would give me an E0 value, or a cell potential value, of negative 1.955 volts. Okay, and so I also asked what type of cell this is, right? If a cell has a negative E value, that means that it is an electrolytic cell. Okay. And so just to do another example, so what is the cell potential of a spontaneous cell containing the following half reactions? Write the proper notation for this reaction. Okay, so here, right, we know we need to change the direction of one of these reactions, right? They're both in terms of reduction now. We have to figure out which one is going to get oxidized. Now, the big hint to help us figure this out is in the first sentence. It says this is a spontaneous cell, or a spontaneous reaction. And we know this only occurs when the cell potential, or E value, for our cell is positive. Okay, so I'd ask myself, for both of these reduction potentials, if I change the sign on each of these, would my overall cell potential be positive? Okay, and so I noticed that if I change the sign of this second equation, and it would become positive 0.7, right? When I solve my my cell potential, my E for the cell value, it would still be negative, okay? While if I change the sign of this top number and add these together, I would get a positive cell potential value, therefore a spontaneous reaction. So that indicates to me that this potassium equation should be the one that's oxidized. Okay, and so that's basically what I did. So down here, you'll notice I rewrote my potassium equation by flipping it. So now I have potassium solid going to potassium plus aqueous plus electrons. You'll also notice that I multiplied it by 3. And the reason for that is when I add that reaction to my other half reaction, the chromium half reaction, when I do that, my number of electrons will cancel. Okay, now this will come back up in a little bit, but you can kind of ignore the multiplying this top reaction by 3 for just a couple minutes. Okay, basically the takeaway was I flipped this potassium equation. So the oxidation potential of this potassium equation is now positive 2.936. My reduction potential of the chromium equation is negative 0.744 still. So when I add my half reactions together, I'm going to add their E values together, and my total cell potential will come out to positive 2.192 volts. Okay, so that's that value. But we were also asked what the standard notation was. Okay, so to figure out my standard notation, I kind of just wrote my overall net equation. So 3 potassium solids plus chromium 3 plus aqueous goes to 3 potassium plus aqueous plus chromium solid. And so from here, I can pretty easily see that my potassium is oxidized, my chromium is reduced. And so remember that in your standard notation, compared to this double line, your oxidation occurs on the left-hand side. So it's going to be potassium solid, line, potassium plus aqueous, double line to now indicate that we're going to the cathode where reduction occurs. And at the cathode, we're going to have chromium 3 plus aqueous get reduced to chromium solid. Okay, that would be the proper notation. Okay, and so again, as you can see in this chapter in electrochemistry, we're going to be flipping equations a lot. We're going to be adding them a lot, right? We add our reduction and oxidation potentials together. And you'll notice that we'll sometimes multiply by coefficients, like I did in that potassium equation. Okay, but it's so important because people forget this all the time, that when you multiply an equation by a coefficient in electrochemistry, there is no change on your E value. Okay, it's unaffected. Okay, now this is a chart that I think can be very helpful, especially for your final. We've learned, going back on the previous slide, I showed you manipulations to E in response to flipping an equation, multiplying by a coefficient, and adding equations together. Now, those manipulations we have also seen in the past for equilibrium and thermochemistry. And so this little chart can just help you kind of separate these and help you remember, based on manipulations, what changes you should make to your equilibrium constant, your Gibbs free energy, or your cell potential, right? And it also reminds you what values of these are spontaneous, right? Negative delta G values are associated with spontaneous reactions. Positive E values are associated with spontaneous reactions. Okay, so again, I think this chart can be rather beneficial, especially on the final, where you might have to do some of these manipulations. And now, you're not just having an exam on just cell potential, it's all of them, and it's kind of easy to get these confused. Okay. So I think there's maybe about 2 topics that we'll cover tonight, and then there's a third topic that I'll push to Wednesday's session. So one of the 2 things that I still want to cover is this, which is a slide covering some of the very important equations in this chapter that integrates cell potential with the other topics that we've learned. Okay, so this top equation relates our delta G naught from thermochemistry to our cell potential. Okay, so delta G naught is equal to negative N times F times our cell potential. Okay, and I'll describe N and F a little bit below. Okay, our other really important equation relates our equilibrium constant to cell potential. So here, our cell potential, E naught, is equal to RT divided by NF times the natural log of K. Okay, now I provided a third equation that's actually the same exact equation as the second equation. Okay, the only difference is I multiply R times T and divide by that constant F to get this 0.0257 volts value. Okay, now something really important to note is you can only use this third equation when you're at 25 degrees Celsius, because that's the temperature they use. Well, they technically use 298 Kelvin, but they're the same temperature. And so what I recommend to students is just to always use this second equation, because if you plug 25 degrees Celsius in, you're going to get this value anyways. I just worry that students will sometimes use this third equation at a temperature other than 25 degrees Celsius, and that will result in an incorrect answer. Okay, so just realize that second and third equation are the same. You can just only use this third equation when you're at 25 degrees Celsius. Okay, now the variables are all listed here. So E naught is our cell potential measured in volts. R is a constant. It's 8.31 joules per moles Kelvin. Our temperature's in Kelvin. N is going to represent the number of moles of electrons transferred during the reaction. And so we will get into this a little bit more on the next slide where we look at an example of that. K represents our equilibrium constant. And then F is Faraday's constant, which is 9.648 times 10 to the fourth joules per mole times volts. Okay, so that F is a constant. Okay, so let's look at an example, and you'll notice that this is the same example as the second example we went through, right? It's the same equations. So earlier, we investigated these half reactions to find our cell potential. Running this reaction at standard conditions, what is the change in standard Gibbs free energy and the equilibrium constant for this reaction? Okay, so at the top, this was what I showed you guys before, right? We changed the potassium half reaction, so it flipped, right? We changed it from the reduced version to the oxidized version. We multiplied it by 3 so that we had 3 electrons transferred in each. And then we crossed them out to get our overall chemical equation. And we added the E values to find our cell potential for the cell, which is 2.192 volts. Okay. Now, we wanted to find the equilibrium constant and standard Gibbs free energy. So to find Gibbs free energy, we're going to use this equation. Negative delta G naught equals negative N times F times E naught. So E naught is the cell potential we solved for above. It's that 2.192 value. F, Faraday's constant, is just exactly that, a constant. So it's going to be that value that was given. But N here represents the number of moles transferred during the redox reaction. And so in this example, it's going to be 3. Okay, and so what I kind of want to make evident is this value N will always be equal to the coefficient of your electrons when they cancel out. Okay, so you have to make sure that you balance your half reactions in a way so that they have the same number of electrons transferred. Okay, so now they both transferred 3, so they're going to cancel each other out. And when they cancel each other out, the coefficient in front of them, 3 in this case, will be your value of N. Okay, and so we plug in all those values. We'll find that delta G naught is equal to negative 6.34 times 10 to the 5th joules, which is equal to negative 634 kilojoules. Okay, so to find our equilibrium constant, we're going to use the other equation that was given, which is our cell potential is equal to RT over NF times the natural log of K. Now, this is being done at standard conditions, so 25 degrees Celsius and etc. So I could actually use that third equation where it's just our cell potential is equal to 0.0259 volts divided by N times the natural log of K. Okay, now in this example, our cell potential is going to be what we found above, 2.192 volts, and N is going to be the number of moles of electrons transferred. So again, it's going to be that value of 3. From here, you do a lot of algebraic manipulation, and we find that K would be equal to E raised to the 255.9th power. Okay, a super large number. Your calculator can't even do it. Just kind of writing it as an expression is good enough here. Okay, but the big takeaway that I want everyone to really understand is how you derive this number N for number of moles of electrons transferred during the reaction. Are there any questions before we cover the last topic for tonight, which will be the Nernst equation? Okay, so if there are no questions, we're just going to go over this last equation, show one example, and then we will wrap up for tonight. Okay, so in thermochemistry, we have this equation, delta G equals delta G naught plus Rn times the natural log of Q, our reaction quotient. And so just kind of remember that we have this equation because delta G and delta G naught are not necessarily the same, right? Delta G is dependent on concentrations and non-standard conditions. Okay, the Nernst equation is extremely similar, right? It's just for cell potential, right? So our standard cell potential, or E naught, is calculated at very specific conditions, right? I believe it's calculated at 25 degrees Celsius at 1 atmosphere pressure for any gases and 1 molar concentration for any anything in the aqueous phase. Okay, now the Nernst equation, this equation you will use anytime your conditions differ from those standard conditions. Okay, so you're going to use it anytime your temperature is not 25 degrees Celsius, or anytime when your concentrations of reactants and products indicate that you're not at 1 molar concentration or 1 atm pressure. Okay, so basically anytime they give you concentrations or pressures or a temperature other than 25 degrees Celsius, you are going to use this Nernst equation to solve for your cell potential. Okay, and so the last example we're going to go through says the below redox reaction occurs in an electrolytic cell. What is the standard free energy associated with this cell? If the same electrolytic cell is examined at 45 degrees, oh, that's not really a complete sentence, but this same electrolytic cell is examined at 45 degrees Celsius. The concentration of sodium ions is 0.39 molar, and the concentration of lithium ions is 0.66 molar. What is the electric potential of this cell? Okay, and so the big key here is they originally tell us this cell is electrolytic. Electrolytic cells, by definition, have a negative E value. Okay, and so I looked at the two half reactions they gave me, right? They gave me Na plus an electron goes to sodium solid, and lithium plus an electron goes to lithium solid. And they gave me the reduction potentials of each. And so I asked myself, which one should I flip and change the sign of so that when I add them together, my E value is negative, right? Because an electrolytic cell needs to have a negative E value. And so I determined that if I flip my sodium equation, that will occur, right? I'll get a negative E cell value. So I flip my sodium half reaction, and so my E naught oxidation value is now positive 2.714 volts. Okay, my reduction potential for my lithium equation is still negative 3 volts or so. And so to find my cell potential, I just add these values together. So my oxidation potential with my reduction potential, and I get a total value of negative 0.326 volts. Okay, and so they asked me, they didn't ask what is the cell potential of this electrolytic cell. They asked what's the Gibbs free energy associated with it. So I'm going to write delta G naught is equal to negative N times F times E naught. Okay, now Faraday's constant is constant, so I'm going to plug that in. My cell potential I just found above, it's negative 0.326 volts. And N here, as you'll notice, in both half reactions, I transferred 1 electron. Okay, so I have the same number of electrons transferred in each half reaction, so they'll cancel out, and their coefficient is 1. So N is 1 here. When I plug this in, delta G naught would be about 31.45 kilojoules. Okay, so that's the first part of the question. The second part asked that if I was at, I believe it was 45 degrees Celsius and some specific concentrations of lithium and sodium, what is my real cell potential, right? Not my standard cell potential, but my real cell potential. So for that, I'm going to use the Nernst equation. And so my real cell potential is equal to my standard cell potential, which is what we solved for above. It's negative 0.326 volts, minus R, which is a constant, times our temperature, so 45 degrees Celsius is 318 Kelvin, divided by N, which is 1, times Faraday's constant, multiplied by the natural log of Q. Okay, and so I just kind of simplified this expression, And when you do that division, it comes out to 0.02739 times the natural log of Q. Okay, now Q, remember, is products divided by reactants. So it's the concentration of sodium divided by the concentration of lithium. So 0.39 divided by 0.66. You take the natural log of it and multiply it by 0.027 or so, and that value comes out to negative 0.0144. Right? And so from here, again, you just kind of do the math out, and you'll find that the real cell potential for this is about negative 0.32 volts, or 31 volts, excuse me. Okay, and so that's how you apply the Nernst equation. Are there any questions on any of tonight's material before I show the challenge problems? And please excuse the couple of slides that we're going to be skipping, but we will get to first thing, or Wednesday. Any questions at all from anybody? Okay, so I'm just gonna kind of put up each slide for about 5 seconds. So try to take a relatively quick picture if that's how you like to do it. If not, remember that these videos are posted. So here's the first problem, which is a true and false about the Nernst equation. Here's a second kind of true question that quite literally gives you almost every possible option. So in essence, this question is A through D, what is true and what's not? It's more select your choice. I just like to make infinite options in multiple choice questions. Okay, for questions 3 through 5, you're going to reference this information here, these half reactions. Okay, so question 3 asks you to write them in their proper notation. Okay, 4 asks for you to, after writing in the correct notation, use that information to solve for the correct reduction potential. Sorry, reduction cell potential. And then 5 asks you to use that information to find your standard change in Gibbs free energy. Okay, and then I believe these are the last 2 problems. Yep. So 16 you can actually ignore. 16, sorry. 6 you can actually ignore. This has to do with that last topic that we were going to cover tonight. However, 7 you can do. 7 is a Nernst equation problem, and I do recommend you do that one for next SI. Okay, so this challenge problem number 6 will be moved to Wednesday's challenge problems because we just haven't covered that topic yet. Okay, and so I'm going to stop sharing my screen and end the recording. But as always, if anybody has any questions, I'm happy to stick around and answer them.